that Darwin's theory works or a proof that it doesn't work. I would be happy either way, but my guess is that it works, although I have some doubts after reading some books I got here in Madrid. There is apparently a wonderful biologist here, not unfortunately in this university, but in the Universidad Autónoma de Mexico, called Máximo Sandin, and he has not only some criticisms of Darwin. A lot of people have some things they don't like about the current neo-Darwinian paradigm, but in fact he has a complete proposal for an alternative mechanism for evolution, which is actually very interesting, and actually has some points of contact, as I realized last night reading a book I got here in Madrid, with the model I'm going to be discussing tomorrow. So I'll be telling you about that, and with a little bit of luck we may. Do any of you know Máximo Sandin? We need somebody we need to contact him somehow because we'd like to talk to him.
Question?
Yes,
yeah.
Question. I guess you'll be addressing this tomorrow, but I'm intrigued. You mentioned fitness. How can a program a fitness? Does it produce itself as an output? Or?
No. Well.
So how is a program fitter than another?
Well, you have to. I'm a pure mathematician, and to get evolution to go on forever, you have to challenge your organisms, right? If your organisms don't have a serious challenge, they'll just watch television all day long and play computer games, and that's it. So you really need to challenge them. So I challenge them by using mathematical problems of the type that Gödel found there are no general methods for. You need to use areas where pure mathematics can prove that you need mathematical creativity. So basically my organisms are pure mathematicians, and I'm taking Gödel incompleteness-like results that certain mathematical questions cannot be solved once and for all. That you can bring to bear an unlimited amount of creativity on some kinds of mathematical questions which are examples of the incompleteness phenomenon. So my organisms are essentially pure mathematicians who are trying to get better and better, but since there is no theory of everything for pure math, there may be a theory of everything for fundamental physics, we hope, but for pure math it's provably not the case. So this is why my organisms will keep evolving forever, because there's always more math for them to discover. That's basically the general outline of how it works. So the organisms will be judged by fitness on how well they do on a few mathematical problems that I'll mention more. One of them is the Busy-Weber problem, if that means anything to you. Naming a very large positive integer, calculating a very large number. That's a very simple example of a mathematical problem that looks sort of trivial, but in fact is deeply connected with Gödel incompleteness and with Turing's halting problem. So that's the general strategy. In other words, in my model, there isn't that big a difference between biological creativity and mathematical creativity.
Has anyone estimated bounds for omega for other than 0 and 1?
Well, yeah. Someone asked, you already asked about that. Yeah. You can do it. I mean, you start looking at lots of small programs and trying to decide whether or not they halt. And that way it is possible to get some more detailed information about the numerical value. But at some point you're going to get into big trouble, which is a consequence of these theorems, and also of the unsolvability of Turing's halting problem, because you can't decide if a program halts or not. You see, but basically to get a good approximation, you would want to look at all programs up to a certain size in bits, decide which ones halt, and that gives you a good approximation. But you can't decide, there is no general procedure for deciding if a program halts or not, which is known from Turing. So people can in various ways try to get estimates, and one of the people, there's a group in, I did some calculations like that. It depends on to get a real estimate, you have to decide, you have to commit to a particular programming language, because remember, the halting probability depends on the programming language you're using. You're generating programs at random, you're having monkeys type a program, and you're asking what is the probability this program will halt. So that depends very much, at least for the initial bits, that depends very much on what your programming language is like, because small programs in most programming languages can't do very much, so you can decide whether or not they halt. But there are some very powerful programming languages where some very small programs actually can do some very sophisticated calculations, and you very quickly are unable to decide if that program will halt or not. So this is the kind of questions you get into.
Another question?
Just one thing. If you take the laws of physics as they are understood now, say the standard model, then it would be simple in yourself because it's made of a few axioms, assuming that there is no problem with the dark mass and things like that. But,
Well, do the laws enable you to calculate the time evolution of the universe? Yes, I guess.
Yes, it would be simple, except if you take into account the uncertainty in quantum mechanics when you do the quantum measurement and the reduction of the wave packet. And as you mentioned in your book, then that would mean that things is very complex. The actual world.
Yeah, this toy model is really, I'm very much thinking in classical terms. So for me, I'm thinking really about a classical universe, and for me a theory is a deterministic theory that gives you exactly your experimental data. But, you know, we know that the physical world is more complicated than that, and you can talk about statistical theories, but it's simpler to really to at least for my purposes, which are proving limitations on the power of mathematics, the simplest thing is to stick with these deterministic theories, where the theory has to calculate exactly the time evolution or your data. So I don't allow statistical theories. Now for applications in physics, you want to discuss that kind of thing, and it can be done, but that's going in the direction of practical applications. So I stopped talking about physics very quickly.
Further questions?
Yeah, to prove theorems, you have to keep these models very simple. So I'm only looking at deterministic theories, you see. So then you have a very simple criteria of what a theory is and how good it is, how simple it is. And then you can prove that you can't be sure you have the simplest theory, the best theory. So I'm trying to keep the model simple so that I can prove theorems. And this biological model is really incredibly simple. But it does have these models do have some interesting properties that you can prove. So that's sort of a new thing, to be able to prove that evolution takes place.
I have one question.
Yes, sir.
You have precise in your model that you will be explaining.
We're going to spend 2 days on metabiology, 3 days on metabiology.
And you have a concrete prediction about the evolution rate.
Right.
Different scenarios.
Right.
So have you thought about going into something practical, something more closer to experiments or something like that?
Well, I think that's a very important question to work on, but I haven't started yet. Yeah, there's some question about whether the evolution that I can prove take place in my model is fast enough or not to sort of make you feel comfortable with living beings here on this planet. And I think that's something we should talk about on Wednesday, to see what you people think about that. So I think it's not clear yet, but I think it's very important to compare these models with what actually happens in biology. You can also do computer experiments of this kind, where you take computer programs and make random changes and look at what happens. So I can think of 2 levels of experimental work that could be done in this field.
Simulation and experiment.
Right, simulation of mutations on artificial software, and then actually real biology. So I think they're both important things to think about and try to do. But this is very early, and so if you have some ideas about that, I would really love to hear about them.
Okay, I think it's been a wonderful lecture. So let's thank the speaker again.
Thanks very much.
There will be the same time, and you will be using also a computer for
Tomorrow, yes.
both the board and computer.
I think tomorrow I won't use the board at all. I think we just need the screen, and I need a computer with an internet connection. So hopefully see you tomorrow.
Visual function.